piece will disappear because I integrate by part and put that b derivative on here, which is 0. So that piece drops away. What else have we got? So this piece, I can put both derivatives on here and then use the de Donde-gauge condition and rewrite this thing as just something like minus m squared pi box h. This thing is just an ordinary, it's just basically the Maxwell-Lagrangian written in Lorentz gauge. This thing, I can put that derivative on here, use the de Donde-gauge condition, for which this then will give the derivative of h. I can take that derivative, put it back, and then by the Lorentz gauge, that will be 0, so that drops out. This thing goes away. And this thing, I can put all these derivatives on here, so that drops away. And so, yeah, so that's a lot easier. And so, to cut a long story short, then, in this gauge, to evaluate the action, you're going to have this part becomes a normal form of the Einstein-Hilbert term in the Donde-gauge, plus a coupling to 2 mu, plus a mixing between pi box h, plus an ordinary kinetic term for A. Now, the purpose of that is to see that this is essentially the kinetic term for the spin 1 part. This is the kinetic term for the spin 2 part. But there's no explicit kinetic term for the spin 0 as it stands. There's no piece like that. But there is a mixing between pi and h. And so what happens is that you can, by performing a diagonalization where you shift h mu nu into h prime mu nu plus e to mu nu times pi, I can remove this mixing term and generate a kinetic term for pi. So the kinetic term for pi comes entirely from here. And in that decomposition, there's an m squared there. So this actually is what is giving the kinetic term for the scalar part. This gives the kinetic term for the spin 1 part. Now, with my kinetic terms, let's now canonically normalize them. So we have these various coefficients running around, which is the Planck mass.
What happened to the second term, the mass square term of h mu nu?
Which, this one?
The up.
This one?
Yes.
Oh yeah, that's still there. Sorry, I just forgot to write that down. So what I'm going to do is now canonically normalize the kinetic terms by doing the standard redefinition. So this is the spin 2 part, its coefficient is the Planck mass. So the canonically normalized fluctuation is obtained by dividing by m Planck over d minus 2 over 2 in d dimensions. So by that, the canonical normalization, this factor disappears in front of here. The canonical normalization of the vectors, you see that the vectors have an m squared times m Planck to the d minus 2 in front. So to canonically normalize the vector, I would divide by, so it's m squared, but there's 2 a's, so I only need to divide by 1 power of n times m Planck to the d minus 2 over 2. Whereas the scalar, its kinetic term entirely comes from here. Now the normalization of h is already determined, so pi has to be canonically normalized. In other words, to get rid of this m squared factor, only pi can make that up because h doesn't have any m squared in it. So the canonical normalization of pi that gets rid of this factor has an m squared on the bottom. So the virtue of that canonical normalization is that these factors go away in front of the various kinetic terms. Now the important point to notice is the m squared here. as we take the massless limit of this theory, let's say for fixed Planck mass, then this term will blow up faster than this and this. So in other words, if we went back to the original field capital H we knew, and we took the limit m goes to 0, keeping m Planck fixed, then we would find that the leading contribution to the metric perturbation would come from du by canonical over m squared m to the d minus 2 over 2. And this is the key to resolving the BDBZ. What it means is that the Listy zero mode becomes strongly interacting at a lower energy scale than the Listy 2 mode. Despite the fact that they're all sitting in the same Poincare multiplet, nevertheless, their interactions come in at physically different scales. And so the dominant interactions in a theory in which the graviton effectively acquires a mass, whether it's a hard mass or a soft mass, resonance like a DGP, the dominant interactions come from the Listy zero mode. And in fact, this prompts us to define a new strong coupling scale lambda, precisely by this relationship, which sets, and so lambda is the scale that determines the interactions of the helicity zero mode. Now a second point we see from this decomposition is that the Listy zero mode enters with two derivatives sitting on it. And so because of that, it has a rather trivial global symmetry that I can take pi, I don't have to put the canonical, but, and shift it by constant and by something linear in x mu. And you see explicitly, because in its definition in terms of capital H, du pi will map under that transformation into du pi because we're taking two derivatives. So something that shifts only linear in x will clearly be leave this thing invariant. And this transformation looks a lot like a Galilean transformation. If you think in the non-relativistic limit of special relativity, you've got the Galilean symmetries. This looks like a Galilean transformation on a field. So this is in fact called the Galilean symmetry. And so what we are deriving is that the in the low energy effective theory, for any theory in which graviton effectively acquires a mass, is basically a Galilean field theory. And a Galilean field theory is a theory of a scalar field defined precisely with this symmetry. And that's how these Galilean theories arise naturally in the context of massive gravity in their decoupling methods. Okay. So let me show you how this works for a very... are there any questions on that? So let me show you how this works for a concrete example of theory in which gravity is massive. So what I'm going to take is an example of a theory in 3 dimensions for simplicity. And it's a theory which is called new massive gravity. And it's a fully covariant theory described by the following action. So it's a 3-dimensional field theory. And the motivation for considering this theory was for ADS-CFT because we can naturally have anti-de Sitter solutions. We had a cosmological constant, but I won't dwell too much on that aspect. So in its original version, that was the theory. So this is a diffeomorphism invariant theory. The Lagrangian is built entirely out of the curvature. So we haven't broken diffeomorphism symmetry. Nevertheless, it will describe a theory of massive gravity whose decoupling limit will give a Galilean. So I want to demonstrate that to you. And the way to do that is to, it's actually easier not to work with this form of the theory, where you've got higher functions of the curvature, but rewrite this in a slightly different way by introducing an auxiliary field.
Excuse me?
Yeah.
What's the motivation for choosing this relative coefficient?
Oh, that'll become transparent in a second.
Okay.
The 3/8, you mean?
Yeah.
Yeah, that'll become transparent.
Right now.
So this theory can be equivalently written in the following form by introducing an auxiliary field. Sigma here is just a constant which you can normalize to 1 or -1 depending on the sign of that term. So we're going to introduce another field, Q mu nu, which is coupled here to the Einstein-Hilbert term. That's G, sorry. So this is an equivalent representation of the same theory. It's got an auxiliary field, but you can easily show that if you look, Q is non-dynamical because there's no derivatives on it. The equation of motion for Q is simply minus G mu nu minus m squared over 2 Q mu nu minus G mu nu Q. And so you can is equal to 0. And so from that you can infer that the trace of Q is minus R over 2m. And you plug that back in, and you find that then this combination reproduces precisely that combination with the minus a third eighth. Now, why did we choose the minus a third eighth up there? It's precisely so that we have the 1 minus 1 here, which is the Fields-Pauli mass term. Okay, so this thing is precisely the thing that's going to give the Fields-Pauli mass term. And so the tuning we're making on that 3/8 is precisely the tuning necessary to make sure there are no ghost degrees of freedom, so that we just have the Fields-Pauli mass term. So let me convince you that this does indeed correspond to a theory of massive gravity, even though it's diffeomorphism invariant. And for that, we simply just need to do the fluctuations around Minkowski space and check what are the physical excitations. So let me do that. So let me, we're going to do G mu nu is E to mu nu plus H mu nu. And then Q mu nu will just, Q is itself small, so we're going to expand Q around 0. Q mu nu is 0 plus Q mu nu. And expand this action out to quadratic order. And for simplicity, I will again choose the Donda gauge H mu nu because it is gauge invariant, so I can do that. Then to quadratic order, this action will simply give, first part will just be the standard Einstein-Hilbert contribution. You should be getting familiar by now if it wasn't before. The second part, this is the Einstein tensor here, so that will give plus 1/2. The Donda gauge, it just works out as plus 1/2 Q mu nu box H mu nu minus 1/2 E to mu nu times H. And then the last term is the last term. That's already quadratic, so we don't need to do anything to that. Well, it's quadratic. We now just put it in the metric G. that's the quadratic theory. And there are two tensors here, and there's a mixing between those two tensors, and so it helps to diagonalize that mixing term, to diagonalize the kinetic term. And that's easy to do by performing the field redefinition. H mu nu is H prime mu nu minus sigma q mu nu. And sorry, I dropped a sigma in front of here. There's a sigma there. And I'm choosing sigma to either be plus or minus 1. And I'll get to what the right choice is in a second, but either way, sigma squared is 1. We perform that redefinition. That removes the mixing term and replaces this by h prime, prime, prime. And then the mixing term disappears and is replaced by minus sigma over 4 q mu nu box q mu nu minus a half eta mu nu q. In other words, we have the standard Einstein-Hilbert kinetic term in the Donda gauge of H prime, the standard Einstein-Hilbert kinetic term for Q in the Donda gauge, and a mass term which makes Q massive. So Q will be the massive graviton, and H prime is a massless graviton. However, we're in 3 dimensions, and a massless graviton in 3 dimensions has no propagating degrees of freedom. Okay, so although this massless graviton is here, there are no actual propagating degrees of freedom associated with it. The only propagating degrees of freedom are those of the massive graviton in 3 dimensions. And so this theory is still fundamentally only a theory of a massive, in which the propagating degrees of freedom is a massive graviton. Now you see there's a sign difference here between this kinetic term and this kinetic term. And one is always a ghost relative to the other. But we could have chosen the sign of sigma so that this one is not a ghost, or this one is a ghost, or vice versa. Now normally we would say if one of them is a ghost, this theory violates unitarity. But in this case, if we choose the sign sigma is minus 1, so that the massless guy is a ghost, and the massive guy is not a ghost, then this doesn't violate unitarity, again because there are no propagating degrees of freedom for a massless graviton. So the fact that the kinetic term is negative does not actually violate any unitarity. There'll be no imaginary contributions in the generating functional because there are no propagating degrees of freedom there. So then by choosing sigma to be minus 1, which is bizarre because we're choosing the Einstein-Hilbert term to be the wrong sign, nevertheless the R squared wins over and makes this into a theory of a massive graviton in 3 dimensions at least. And you can see why you can't do this in high dimensions, because in high dimensions this would be propagating and then you really would violate unitarity and that would be the end of the story. Okay.
Sorry.
Yeah.
But if I put it on the area space,
yes.
Somehow I would expect that this massless graviton would somehow correspond to some boundary degrees freedom. Was that the sign flip somehow resulting in some non-unitarity?
It does, yeah.
Okay.
Yeah. But that's that's a whole other level of argument than what I'm doing here. But yeah, you're right. It does ultimately so this theory it does ultimately violate unitarity, but not for perturbation. No, it doesn't violate unitarity for perturbations around Minkowski.
Okay.
Yeah. But you're right. But that's a whole different story. But for my purposes, I just want this as an illustrative example of how the Galilean will arise in its decoupling limit, because this is fundamentally a theory of massive gravity. In the case of the other massive gravity theories that we'll talk about and that Rachel will talk about, there is no ghostly massless guy. There's just a right guy. Okay. So let me try to illustrate to you where the Galilean comes from in this theory. And so there's my theory, back in its fully nonlinear form. Now what I'm going to do is to basically want to do some analog of the Stuckelberg trick, which is just a field redefinition. This is now this is a nonlinear, fully covariant theory. And the trick to notice is that because of this coupling, as everybody knows, the covariant derivative of g mu nu is equal to 0. And so because of that, I can shift q mu nu, define a new field, q tilde mu nu. I can shift that by any covariant derivative of a vector, symmetrized. And in this term in the action, that won't do anything, because this will just give me a derivative of a times g mu nu. I integrate by parts. The derivative gives me 0, because this is identically conserved. And so that will leave that piece unchanged. And then this will do something extremely analogous to what we had before in the mass term. Just now, a covariant nonlinear version of that. So that is basically introduced a linear d in d dimensions, linear diff symmetry. So that's the extra symmetry that we need to introduce in order to properly view the massless limit of this massive graviton theory. So you should not confuse this linear diff symmetry with the actual three-dimensional nonlinear diff symmetry. It's a completely separate symmetry because we have two gravitons here. So the massless graviton has its own symmetry, which has to be realized as nonlinear diffs by the Weinberg, Faser, etc. arguments. But we have a separate massive graviton, which doesn't have a symmetry, but in order to see the massless limit, we have to introduce an extra linear diff symmetry. And that's how we do it here. And then also I want to introduce the extra U1 symmetry that describes the Listy zero mode. And I do it like that. And then same story here, that won't give any contribution inside here. And that introduces the extra U1, just as we had before. And then I should canonically normalize these pieces. And the canonical normalization that's helpful in 3 dimensions, we put an m squared with this one. We put an m with this one with the square root of m3. And with this one, we just have the square root of m3. So that's the same story as before, just the 3-dimensional version of it. The Listy 0 mode has a 1 over m squared, the Listy 1 mode has a 1 over m, the Listy 2 mode doesn't have anything. And so just as before, as m goes to 0, this guy will be the one that gives the dominant interactions in the mass term. So if I do that, it gets messy again, just like before. So let me try to skip to the essential details rather than boring you with the whole calculation. So after this redefinition, this part doesn't do anything. I'm going to put the m3 there. And there's a square root of m3 here. And then all the complicated stuff is in the Fields-Pauli mass term. And these are all covariant derivatives. Squared minus itself again. Now, as before, when we square this out, we're going to get lots of terms. Let me focus specifically on the contribution coming from pi. So the leading contribution from pi will have an overall, I've taken the m3 in, because the square root of m3, so it'll be an m squared, there'll be an overall 1 over m squared. So the leading contribution, there's a reading contribution is 1 over m squared d mu pi d mu pi minus minus box pi squared. Now, before when we had this piece, we were looking at this in Minkowski space. These weren't covariant derivatives, these were ordinary derivatives. And in that case, this was a total derivative, and so we just threw it away. In the present case, it's not a total derivative because these are covariant derivatives, and covariant derivatives don't commute with each other, and they don't commute with each other up to the Riemann curvature. And in this case, after integration by parts, this combination becomes 1 over m squared r mu nu d mu pi d nu pi. And that piece will survive as a non-trivial interaction. Okay, so, and then we've got all the other junk. So what will happen, we'll get the a squared terms. Those will package up to give you the Maxwell Lagrangian. We're going to have the q squareds, which will just give you the Fierz-Pauli mass terms. And then there'll be various annoying cross terms. But to see the interactions in this theory, I'm now going to take the following coupling or scaling limit. So we're going to take the limit m goes to 0, because we want to think about the v dv z and how that gets resolved. So we want to take the m goes to 0 limit of this theory, but keeping the interactions of the Galileon, which I told you would come in general dimensions. It's 2 plus d minus 2 over 2. So in the present case, it's 2 plus 3 minus 2 over 2. Times 3 minus 2 over 2. In other words, it's lambda is m squared square root m3 to the 2/5. So what I'm going to do is take the parameter m to 0 at the same time as taking the three-dimensional Planck mass to infinity, keeping this scale fixed. So this is sometimes called a double scaling limit. Because we're doing two different scalings, keeping one combination of those scalings fixed. In that double scaling limit, what will happen is that the LISI2 and the LISI1 modes will completely decouple. Not completely, they will in a second, but I should get to that. So in that limit, what we're going to do is take the metric g mu nu and write it as e to mu nu plus h mu nu over the square root of m3. That's the canonical normalization for the metric perturbation. So r mu nu in that limit is going to give something that will scale like r mu nu basically is box h mu nu plus dot dot dot. That'll have a 1 over square root of that. Well, yeah, let me know it's not box, it's the Lichnerowitz. We're speaking as the Lichnerowitz operator. 1 over square root of m3. So in the decoupling limit, m-Planck is going, m3 is going to infinity. So this piece by itself is going to 0 because we're sending m3 to infinity. But m is also going to 0. And we see that what we've got, the combination is m squared times square root m3. And that's precisely this interaction scale, which we're keeping fixed. So then in this limit, this non-trivial interaction, which is cubic interaction, remains finite in that limit. So to cut a long story short, then once you've taken that decoupling limit, then what you get is this D2 mode coupled to Q tilde and